Good day, everyone. Today I'm going to discuss the fundamentals of contact lens prescribing. I'm Dr. James Abraham Lee from the sections of Pediatric Ophthalmology and Strabismus and Optics, Refraction, and Contact Lens of the UPPGH. There are three basic contact lens parameters: the base curve, the diameter, and the power. The base curve is the curvature of the central part of the posterior surface of a lens. It is reported in millimeters or in diopters. The diameter is the maximum edge-to-edge width of a lens. RGP, or rigid gas permeable lenses, have a diameter between 9 to 9.8 millimeters, while soft contact lenses have a diameter between 13 to 15 millimeters. And the power, as we all know, can be minus or plus. Other contact lens parameters include the central thickness, which is the distance from the back surface to the front surface of the lens, the DK value, which is a measurement of oxygen permeability, and the DK over L value, which is known as the oxygen transmissibility of the lens. First, we discuss fitting of soft contact lenses. Soft contact lens fitting can be divided into three steps: determining the keratometric readings or base curve, measuring the corneal diameter, and determining the power. To determine the K reading, you may use an autokeratometer or a corneal topography machine as in this example. This will give us the contact lens base curve. In soft contact lenses, you have to fit flatter than the flattest K reading. Remember that the flatter meridian is the one with the lower diopter value and the higher base curve. For this example, we are given two K values, 47.91 and 43.27 diopters. Since 43.27 is the flatter value, we choose this as our base curve. Converting it into millimeters gives us 7.80 millimeters. However, since we need to make it flatter than this, we add 0.7 to this value. For this example, 7.8 millimeters plus 0.7 gives us a base curve of 8.5 millimeters. So, how do we convert diopters to millimeters? The radius of curvature formula is the result of the difference between the refractive indices of two media divided by the diopter power. For our use, we use the index of refraction of the cornea, which is 1.3375, minus the index of refraction of air, which is 1, divided by the diopter power, and multiplied by 1000 to get our base curve in millimeters. Once you have your base curve, the second step involves measuring the corneal diameter. It is important to measure the HVID, or the horizontal visible iris diameter of your patient, in millimeters and adding 2 millimeters more to it to make it bigger than the cornea. After this, you determine the power of the lens. In patients whose astigmatism is less than 1/4 of the spherical power, you may disregard the cylinder power or convert it into a spherical equivalent. Before choosing the lens power, remember to crack the refraction and use the vertex distance formula as necessary before combining to get a final refraction. What does this mean? So let us review some concepts. The vertex distance formula is your diopter power squared divided by 1000 multiplied by the vertex distance, which is the distance of your cornea to the back surface of the spectacle lens. This value is usually between 10 to 12 millimeters. You have to remember that converting a spectacle refraction to a contact lens refraction could result to a more hyperopic refraction, while converting a contact lens refraction would result to a more minus refraction when giving spectacles. To remember this, remember the mnemonic CAP-FAM. Closer, add plus; farther, add minus. We only do vertex distance compensation in refractive errors for diopters and above, as this will already have a different value when doing the vertex distance formula. Powers below 4 diopters will have a negligible effect as seen in this conversion chart. Separating your spherocylindrical refraction into two spherical values can be done by copying your sphere and reversing the cylinder axis. In this case, minus 2 diopters at axis 180, then adding the cylinder power algebraically to your spherical power. And in this case, that's minus 1 diopter plus minus 2 diopter, which gives us a value of minus 3 diopters. And just copying the axis of the original cylinder power, which is 90 in this case. So why is this important? Why is cracking or separating your spherocylinder formula important? This is important because there are certain spherocylinder refractions, such as this at first glance, that seem to only need vertex compensation only for the power larger than 4 diopters. However, as you can see, when you separate or crack it into two spherical powers, both values need to be converted. In this case, minus 5 diopters will become minus 4.75 diopter sphere, while minus 7 diopters will become minus 6.5 diopters when vertex distance compensation is done from a spectacle refraction to a contact lens refraction. And once you have these new values, you can combine them again to get your new vertex compensated spherocylinder refraction. So how do you convert? And how do you combine? First, you copy the more positive number as your sphere, in this case, minus 1 diopter. Then you subtract algebraically the copied sphere from the other sphere, in this case, minus 2 diopters minus minus 1 diopter, which will give a value of minus 1 diopter. And then just copy the axis from the more negative sphere. So the spherocylinder refraction for these two values is minus 1 diopter sphere with minus 1 diopter cylinder at axis 180. Now back to our previous example, we use minus 4.75 sphere as our sphere because it is the more plus value of the two. We subtract algebraically minus 4.75 diopters from minus 6.5 diopters, which gives us a value of minus 1.75 diopters, and we get the axis of the more negative sphere, which is 180. So, from the original refraction of minus 5 diopter sphere combined with minus 2 diopter cylinder at axis 180, the vertex distance compensation would lead to a new refraction of minus 4.75 diopters combined with minus 1.75 diopter cylinder at axis 180, which is less minus because we brought a spectacle refraction closer to the eyes by prescribing a contact lens. A good fitting soft contact lens should have sufficient movement of 1 to 2 millimeters when blinking for proper tear exchange to provide oxygen to the cornea. It should center after each blink, provide stable, clear vision, and have a good retinoscopic streak. If movement is too much or does not center after each blink, the contact lens is loose. If it doesn't move, it is too steep. Increasing the diameter or decreasing the base curve tightens a loose contact lens, while decreasing the diameter or increasing the base curve loosens a tight contact lens. Patients who have loose-fitting lenses will experience variable vision and bothersome lens awareness, among others, while those who have tight-fitting lenses experience fluctuating vision, decline in comfort, eye redness, and burning sensation. Again, patients with good-fitting lenses will have sufficient movement, proper centration of the lens, stable vision, and a clear retinoscopic reflex and keratometric mirrors. Also remember that your contact lens should be bowl-shaped and not inverted. Next, we go to rigid gas permeable lens fitting. Although not any more widely used compared to the soft contact lenses, RGPs provide good quality vision, are durable, and have high oxygen permeability. Aside from this, they are able to correct moderate amounts of astigmatism and corneal irregularities secondary to a tear lens interface between the anterior cornea and the posterior surface of the lens. You must also choose the lens material and type based on its permeability, wettability, and durability. In fitting RGPs, you also need an RGP trial fitting set with the different base curves. You need to evaluate the fluorescein pattern, the lens movement and position, as well as the visual acuity and comfort of your patient. Unlike the soft contact lens where we choose a base curve that is flatter than the flatter K reading, in RGPs, we start fitting on the flattest K reading. Not only do we measure the HVID, but we also measure the pupil size and the palpebral fissure. Determining the pupil size is important in determining the optical zone diameter because a dilated pupil in dark conditions that is bigger than the optic zone diameter will experience flare or halos reflections around the lens. The diameter of your RGP should be 2 millimeters smaller than your HVID to allow it to move vertically and horizontally without impinging on the limbus. For example, if your HVID is 11.5 millimeters, the RGP should have a diameter of 9.5 millimeters. Just like your soft contact lens, determine if vertex distance compensation is needed for your refraction. You can disregard or convert into spherical equivalent cylinder powers that are less than one-fourth the value of your sphere. For RGP fitting, it is important to do an over-refraction once the base curve has been chosen. Each trial lens set will have a certain power in the lens. Do the refraction with the lens placed on the eye of your patient and determine the new refraction. For example, if a trial lens set has a power of -3 diopters and you get a refraction of -2 diopter while the patient is wearing the lens, then the final refraction is -5 diopters. However, if a trial lens has a power of -3 diopters and you get a refraction greater than 4 diopters, then you still need to do vertex compensation for the refraction greater than 4 diopters and add it to the power of the trial lens that the patient is wearing. For RGPs, aside from checking the position and movement of the lens when blinking, we also check the fluorescein pattern. In a loose-fitting lens, you can see dye pooling on the periphery, such as in this picture, while a tight-fitting lens would have a central pooling of the dye as seen in this picture. Patients with astigmatism will have a dumbbell-shaped pattern, while a good-fitting contact lens will have a more or less good dye coverage with minimal apical and peripheral pooling and should center after each blink. So this is just an example of a good-fitting contact lens. You can see that it has good movement and it centers after each blink. So in summary, in soft contact lenses, you should fit flatter than the flattest meridian, then the diameter should be 2 millimeters more than the HVID. While in rigid contact lenses, you will need a trial fitting lens set, start fitting on the flattest meridian, and adjust as necessary. RGPs are usually 2 millimeters smaller than the HVID. Once with the right base curve, do over refraction to determine the patient's new refraction. Evaluate the fluorescein pattern and observe the lens movement and centration. I would like to acknowledge Dr. Romy De La Cruz and Dr. Ermita for their inputs for this lecture. Thank you very much for listening and have a good day ahead.